Hi, my name is Ellie Rich, and this is my Georgia Tech Physics 2211 Lab 1 Constant Velocity. In this lab, I studied how an object moves when it has constant velocity and compared my experimental results to a computational model. In this presentation, I will go over an introduction to the physics concepts, the mathematical models used, the experiment itself, the glow script coding, a discussion of the data, and finally my conclusions. The goal of this experiment was to study motion at a constant velocity, meaning there is no net force acting on the object and no change in direction. The object I used was an expo marker rolling across a flat surface. I compared the real motion of the marker to a computer simulation to see if they matched. The main physics concepts used in this lab were Newton's first law, Newton's second law, and constant velocity. Newton's first law says that if there is no net force, nothing changes. An object in motion continues moving at the same speed and in the same direction. Newton's second law states that F equals m times a. This means force equals mass times acceleration. If acceleration is zero, then the net force must also be zero. Constant velocity means net force equals zero, speed stays the same, and direction stays the same. To model the motion, I use three main equations. First, the velocity update formula, where V final equals V initial plus net force over mass times delta t. Since the net force was set to zero, velocity stayed constant in the simulation. Second, the position update formula, X final equals X initial plus velocity times delta t. Third, average velocity. Velocity equals change in position over change in time. The slope of a position versus time graph gives the velocity. This graph shows position versus time. The line is straight, which tells us the velocity is constant. If the object were accelerating, the graph would curve, since its linear acceleration is approximately zero. The system in this experiment is the expo marker. The surroundings include friction, air resistance, gravity, and the surface it is rolled on. I use Tracker to measure the experimental position. I use GlowScript to create the predicted position. Then I used Excel to compare both sets of data. First, I recorded a video of the expo marker rolling across a flat surface at a steady speed. Next, I uploaded the video into Tracker and measured the marker's position at equal time intervals. Then I used the GlowScript starter code and entered my measured values. Finally, I graphed both the experimental and model data in Excel to compare them. This slide shows how I set up the coordinate system in Tracker. I used a scale reference to convert pixels into meters and tracked the marker frame by frame. This allowed me to determine position over time. From Tracker, I found the initial position was 0.00270 meters in the x direction. The total time of motion was 0.7 seconds. The initial velocity was 0.4459 meters per second in the x direction. I calculated velocity using the first two time data points. At time 0, the position was 0.00270 meters. At 0.03333 seconds, the position was 0.01757 meters. Using change in position over change in time, I got approximately 0.4459 meters per second. In GlowScript, I set net force equal to 0, mass equal to 1, initial position at 0, initial velocity equal to 0.4459 meters per second, delta t equal to 0.033 seconds, and I ran the simulation until 0.7 seconds. Because the net force was 0, the velocity remained constant throughout the simulation. This graph compares the experimental and model positions. Both lines are straight and have nearly the same slope. This shows the marker moved at a constant velocity with zero acceleration. The small differences are likely due to real-world effects not including the simulation. Possible sources of error include friction, air resistance, or a slightly uneven surface. There may also be small tracker errors or an uneven push. The simulation assumed no friction, which could explain for small differences. If the axes were reversed, the slope wouldn't be negative, but the graph would still be linear. Zero net force does not mean no forces are acting. It means the forces are balanced, so acceleration is zero and velocity stays constant. The experimental results closely match the computational model. This shows that the expo marker moved with constant velocity and experienced zero net force. Therefore, Newton's second law is supported.